Welcome, everyone. Last time, we explored how forces do work in moving objects. Today, we start our journey into kinetic energy, the energy an object has because of its motion. Imagine riding a bike. The faster you pedal, the more energy you feel. This energy we call kinetic energy. Mathematically, kinetic energy is given by the formula K equals 1/2 mv squared, where m is the object's mass and v is its velocity. Here, velocity is squared, meaning speed affects energy significantly more than mass. Kinetic energy is a scalar, so it only has magnitude. It doesn't point anywhere, unlike velocity. It's a measure of the work the moving object can do on other things, like how a fast-moving car can crash with great force. Keep this concept in mind as we explore examples and see kinetic energy in action. We'll connect these to the work-energy relationship and prepare to understand work done by forces that change with position, leading us into calculus ideas. Let's dive in. Let's take a closer look at the kinetic energy formula. K equals 1/2 mv squared. Why is velocity squared? Imagine you double your speed. Your kinetic energy becomes 4 times greater because velocity is squared. This nonlinear effect shows velocity's influence dominates. Compare this to how doubling mass only doubles kinetic energy. This explains why even small objects moving very fast can have large kinetic energy, like a bullet. Also, kinetic energy directly relates to how much work an object can perform due to motion. So, understanding this formula lays the foundation for analyzing energy transfer in physics. Keep this powerful relationship in mind as we examine real-world values of kinetic energy for different objects. Here is Table 5.2, presenting typical kinetic energies for different objects. The first column names the object, from a car and running athlete to tiny air molecules. The second column lists mass in kilograms, the third, the speed in meters per second, and finally, the kinetic energy in joules computed by applying the formula we learned. Notice a car with mass 2,000 kilograms at speed, 25 meters per second, has kinetic energy of about 6.3 times 10 to the fifth joules, a huge value. A bullet, although small mass, 0.05 kilograms, moving very fast at 200 meters per second, has significant kinetic energy around 1,000 joules. Even raindrops and air molecules have kinetic energies, though tiny due to their speed. This wide range demonstrates how combinations of mass and velocity determine kinetic energy magnitude. Understanding these numbers helps us appreciate energy in real-world systems, from sports to nature to machines. Next, we'll work through an example, applying this formula to a bullet's motion with energy loss. Let's apply kinetic energy concepts to a practical example involving a bullet. The bullet weighs 50 grams, or 0.05 kilograms, and initially travels at 200 meters per second. It passes through 2 centimeters of plywood, losing 90% of its kinetic energy, but retaining 10%. First, we calculate initial kinetic energy. Half times mass times velocity squared equals 0.025 times 40,000, giving 1,000 joules. The bullet keeps only 100 joules after passing through, so its final kinetic energy is 100 joules. Now, speed depends on the square root of kinetic energy divided by mass. We solve V final equals square root of 2 times kinetic energy final over mass, which is square root of 4,000, or 63.2 meters per second. Notice speed drops about 68%, but not 90%, because of the square relationship in the formula. This illustrates how energy loss translates into less drastic velocity reduction. Understanding this is vital in ballistics and shows why kinetic energy formulas allow deeper insight into motion after collisions or resistance losses. We'll build on this understanding when exploring work done by forces that vary with position. So far, we looked at work done when a force is constant, using the simple formula work equals force times displacement. But what happens if the force changes as the object moves? This situation is common in real life. To handle this, imagine breaking the total movement into many tiny steps, each so small that the force doesn't change much over that tiny part. Then, work done in each part is approximately force at that point times the tiny displacement. Adding all these pieces together approximates total work done. This idea sets the stage for calculus introduction, where the sum becomes an exact integral as the slices get infinitely small. This foundational idea opens up powerful tools for dealing with forces that vary constantly in more complex physics. Let's interpret the expression for total work as a sum from x initial to x final of force at position x multiplied by a small displacement delta x. The capital sigma symbol means add all these terms together. Each term represents work done over a tiny slice of the path where force is nearly constant. As we use finer divisions, the delta x getting smaller, the approximation improves. Physically, this is like counting the work done in each tiny step and adding it up to find total work. This summation is fundamental in physics because often forces change with position, and summation is the bridge to more precise tools, namely integration. Next, we'll formalize this process with limits, connecting to integral calculus. To find the precise work done by a force that changes with position, we take the summation approach further by making the displacement segments infinitely small. As delta x approaches 0, the number of terms in the sum increases without limit, but the sum approaches a specific value. This value equals the area under the force versus displacement curve, represented mathematically by an integral. So, work done is the integral from the initial position x sub I to final position x sub f of the force function f of x integrated with respect to x. This powerful tool allows us to exactly calculate work in real scenarios where forces vary continuously. Next, we'll see how this integral appears graphically and work through an applied example with varying force. Here is a graphical representation of force as it varies with displacement. The force function f of x forms a curve, not a flat line, showing changing force values. A small section of the curve is approximated by a narrow rectangle whose height is force value at that position, and width is a small displacement delta x. The area of this rectangle, force times displacement, is the small work done over that segment. Adding all these small rectangles sums up to approximate the total area under the force curve from start to finish. As these rectangles get thinner, the approximation improves until the sum equals the exact work done. This area interpretation of work is a visual way to understand the integral formula we discussed. Visualizing work this way connects the abstract integral to a concrete area under a curve concept. Let's analyze a real-world problem illustrating the work done by a varying force and friction. A woman pushes a trunk over a rough railway platform, covering a total distance of 20 meters. Initially, she applies 100 newtons of force, which remains constant for the first 10 meters, then decreases linearly to 0 from 10 to 20 meters. The opposing friction force is constant at 50 newtons. To find the work done by the woman, we look at the force versus displacement graph. The area under her force curve splits into two shapes: a rectangle for the constant force over 10 meters, and a triangle for the decreasing force over the next 10 meters. The rectangle's area is height times width, 100 newtons times 10 meters, equal to 1,000 joules. The triangle area is half base times height, half times 10 meters, times 100 newtons, equals 500 joules. Adding these, the woman's work done is 1,500 joules. The frictional force opposes the movement and acts over 20 meters with constant magnitude. Its work is force times distance, but negative because friction removes energy. So, work by friction is negative 50 newtons times 20 meters, negative 1,000 joules. These calculations illustrate how summing areas under force displacement graphs gives total work done for changing forces. We see work done positively by the woman adding energy, and negatively by friction drawing energy away. To conclude today's lesson, let's summarize core ideas. We defined kinetic energy as the energy of motion given by 1/2 the mass times velocity squared. We explored that kinetic energy is scalar and heavily influenced by speed because velocity is squared. We then connected work to energy transfer, showing how force times displacement does work, changing an object's energy. When force varies with position, we saw how summing small contributions over tiny displacements leads to an integral calculating total work. This integral represents the area under force versus displacement graphs, a powerful graphical interpretation. Our example involving the woman pushing a trunk illustrated work done by varying force and friction, reinforcing that positive work adds energy, while negative work removes it. These principles set the stage for understanding the work energy theorem, showing that net work causes change in kinetic energy, which we will explore next. Keep these fundamentals in mind as we continue to investigate energy and motion in physics.